Okay, so let's start with a quick recap. All right. Last week, we looked at neural networks with one hidden layer. Let me just move this out of the way. Okay, and those neural networks we said were special because they were able to learn not only, let's say, a mapping from features to classes or from features to a continuous output, but they were also able to learn a feature representation. So for kind of a quick review of where we are in terms of the evolution of learning models. So you might remember we started off the semester talking about this example from the 1964 World's Fair of handwriting classification. And in that example, we would take some input. Green. So in that example, we take some input like a handwritten digit. And you could see, if you kind of take a look back at this example we looked at, the next step after taking the input was extracting features from the input. Right? So in this case, the features were which strokes were located in which parts, let's say parts of the image grid. So for this handwritten digit classification problem in 1964, they would take the input, extract the stroke information as features. And the designers of this algorithm kind of explicitly handcrafted rules for extracting features from the image. So these are kind of handmade features. And after extracting the handmade features, they would then apply handmade rules for determining, let's say, which combinations of features indicated which images. So for example, if you saw certain strokes in certain parts of the image, they had a series of logic gates in a circuit for doing the classification based on the feature value. And again, those were handcrafted rules for mapping from features to output. Okay, so finally we had the output. Okay, that was for rule-based systems. Then we introduced some classical machine learning methods. And the classical machine learning methods, what part of this is now going to be learned instead of handcrafted? Okay, I'm going to rename this to a handcrafted mapping from features to output. With our classical machine learning methods, such as the logistic regression, for example, we had a learned mapping from feature values to output. Right? So you may recall, let's see if we could pull up an example. Let's say from homework 4. Right? The logistic regression classifier would learn. Oops. Let's go back. Okay. The logistic regression classifier learned kind of a series of rules for each class that said, okay, if you have a pixel here, that maps to higher probability of this class. If you have a pixel in this other location, maps to a higher probability of this other class. So the logistic regression and other classical machine learning methods would learn the mapping from feature values to particular output. Then we have our neural networks, which adds a kind of representation learning. Okay. And when I say representation, I mean a representation of the input. Okay. So now, not only is the mapping learned, we said last week, that you can learn the mapping of, let's say, feature values to a particular output, but with a neural network, you can also learn a representation of the data. So the early layers of the network, or the hidden units in the network, learn a representation of the feature that's more amenable to classification or regression. And the last part of the neural network does the mapping from feature values to class or to continuous value. So moving back here. So now we have learned features. Okay, so we have this fabulous evolution where we started with, handcrafted features, handcrafted mapping. And then we move on from there to kind of handcrafted features to learned mappings and these classical machine learning methods. And then we have neural networks where we can learn the features and also learn the mapping. Then the question is, where do you go from there? Well, let's take a look, for example, okay, let's look at what we can do with a single layer hidden network with many nodes, okay? So suppose I have some function that looks like this. Okay, so I have a one-dimensional function x, y. Okay. All right, so I have this function, let's draw it a little better. All right, I have this function f of x, and suppose I want to try and learn this with a regression. Can I learn this function with a single layer neural network? Well, if the neural network has a nonlinear activation function, then we absolutely can. So let's take a look at what we might do, right? So suppose we're using a sigmoid activation. Okay. Now I'm going to focus for a moment on just learning this part of the function. I want to learn that for this range of x, the value should be this value of y. Okay. So I want to learn that particular value. Can I create this little bump at that particular position with the sigmoid activation function? Well, let's see. So I have this x-axis, right? And I want to create this bump. Now, can I kind of make an increase happen at that particular point in the x-axis? So I can adjust, let's say, the output of my neural network. Okay, so let's imagine I have a neural network. I have a unit, which is represented by the sigmoid activation function. And the input to this unit is going to be x. Right? And then the output of the unit will be the output of this sigmoid function. And I'm going to learn a weight. And I'll also learn a bias, right? So a bias weight. Okay. So one thing I can do is I can adjust the bias weight in order to kind of shift where the increase happens along the x-axis, right? So currently, let's say my output is just a sigmoid, right? So it will be, a sigmoid like that. If I adjust the bias term, I can adjust where that increase happens along the x-axis. So I can take a sigmoid and move it anywhere along the axis by adjusting that bias. Okay. So I want the first increase, I want to, let's say, represent just this little bump. So I'm going to move that sigmoid to right where that bump should go. Okay. Now, I want to make the height of this bump be exactly equal to what the value of y should be for this value of x. Can I do that? Can I make the value of the increase adjust to this height? What do I need to change in order to do that? Okay, so I can adjust the weight. So if I adjust this weight parameter, then I can scale this. All right. Okay, what else can I do? Well, suppose I want to kind of represent this function as a series of such bumps. Right? So maybe the first sigmoid should represent the first part of the bump. maybe I want another one representing the second one. So I want to represent this continuous function using a sequence of these bumps. Well, I have one sigmoid right now. I can adjust where it is on the x-axis, and I can adjust its height. Now, I can also, let's say, add another layer here. I'm going to add another neuron here. Okay, and this one also has a weight, a bias weight, of course. I can keep adding as many bumps as I want, and I can adjust their position along the x-axis, and I can adjust their height. So I can put these together in kind of any way I want so that their weighted sum at the output can create as many of these little bumps as I need. And I can then approximate any continuous function to some desired degree of accuracy. Now, the more accuracy I want, the more sigmoids I need, because I need then these kind of different bias weights to be very close together. Right? So if I need these to be very close in order to approximate small changes, I need a lot of these hidden units. But if I have sufficiently many hidden units, I can approximate basically any function meeting some reasonable conditions to any degree of precision that I want, just by accumulating many of these bumps. So a single layer hidden network is what's known as a universal approximator. This is actually the second model we learned that's a universal approximator. The one nearest neighbor is also a universal approximator. But we can approximate virtually any function. So does that mean we're done? Well, not exactly, because just because we can approximate any function, all that means is that there is some set of weights and bias weights that exist that would allow us to approximate any function, any function meeting the requirements, as a series of these little bumps. But that doesn't mean that we have a good way to actually learn those weights and biases. So it turns out that, first of all, it's not clear exactly how many of these hidden units you need in a single hidden layer in order to approximate a particular function. But it turns out that the number of hidden units you need tends to grow pretty quickly with the kind of complexity of the function and the precision you want. And also, we don't necessarily have a good way to learn those weights that approximate the desired function. So a hidden network with a very large, hidden layer with a very large number of units can become unwieldy and kind of difficult to treat. Now, it turns out there is a better way. And the better way is what's known as deep learning. So what is deep learning? So in deep learning, I still have an input. I still have some learned features. But now I'm going to have multiple layers of learned features. So instead of just taking, let's say, one set of inputs, learning some simple features. So we know that, let's say, each of these individual units only produces kind of a linear classifier output, like a sigmoid output, or some other nonlinear function. But the output of a single node in the feature space is basically similar to like what a logistic regression would produce. So each of these hidden units produces kind of a very simple feature. With deep learning, we take those simple features and then we combine them using, let's say, a linear mapping and a nonlinear activation too. And then we can learn much more complex abstract features from the combination of simple features. So now we're going to have learned simple features, but also learned complex features. So this is what deep learning is all about. Okay. We've gone from this, let's say, rule-based paradigm where we have to handcraft features and then handcraft mapping to this deep learning world where not only can we learn features, we can learn very complex representations of the data by learning combinations of features that are useful, and then also learn the mapping. Okay, so with a deep neural network, not only are the features learned, but very complex features can be learned. Let's draw our deep neural network. Okay, so I'll have maybe a network with 2 inputs. Okay, a few hidden units. And this is a fully connected network, which means that in between a layer, every node is connected to every other node in the next layer. I'm going to add my bias node up here. Okay, so that's kind of a node that I just use for learning the bias term. Now, in the old regular learning world, I would just take these neurons and map them to some output, again, with a bias term. But now, in my new deep learning world, I'm going to add another layer of hidden units. And this layer of hidden units behaves exactly the same as the first layer. So along each of these lines, I'm going to learn a weight. And at the input to the unit, I'm going to take a weighted sum of those inputs. Then I'll apply an activation function. And that activation function will then be the input to the next layer. And I can repeat this as many times as I want. And every time I do, every time I repeat these steps, I'm just going to keep pasting copies of layers on top. Each layer now has the benefit of the features learned by the previous layers, and they can now learn very complex representations. So they can learn much more advanced features. And again, my output node works exactly the same way. So everything works the same way. At the input to each unit, I take a weighted sum of the outputs of the previous units and of the previous layer. And then I apply an activation function, and that is the output to the next layer. And at the output unit, I will either apply a classification sigmoid function. I might apply softmax if I have a multi-class classification, or I might use a linear activation function at the output if I have a regression problem. How do I train this neural network? Well, it's exactly the same way. So for inference, I'll do a forward path on the network. And for training, I'll do a backwards path. Okay. Recall from last week, we talked about backpropagation. And backpropagation, I start at the output unit. I compute the derivative of the loss function with respect to the input at that unit, which includes the weights. Right? And I have some backpropagation error at each unit. And then that backpropagation error, those little delta terms, propagate from the output back towards the input unit. So when I compute the gradients at every unit for gradient descent, I'm going to compute the local gradient, right? So the local gradient has 2 parts. Let's remind ourselves why not. Okay, so at every unit, I will compute the local gradient. So the local gradient is the derivative of the activation function with respect to the inputs at that unit. And then the derivative with respect to the weights coming into the unit of everything coming from upstream. Right. So this is a sum over everything coming from the next layer. Okay. So for example, if I'm at this particular unit right here, when I'm training the network, I'll compute the derivative of the activation function of this unit with respect to its input. And then I'll multiply that by the upstream derivatives. So everything coming from these nodes over here. Okay. So I'll compute a local derivative with respect to my inputs here, multiply that by the upstream derivative, and then I'll propagate that back to all of the nodes that are connected to me. These are my downstream nodes. Okay, so there we go. So derivatives are computed in a very similar way as back propagation. So I compute my error at the output, I propagate it back towards the input. Okay, some other comments. Every layer is still fully connected to the next layer. Every unit still works the same way. We still train the network by back propagation. You might hear some reference to the depth of the network. So that's the number of layers, usually the number of hidden layers. And each layer has a width. That's the number of hidden units in the layer. Okay, so what are the challenges with deep neural networks? I listed two challenges, optimization and generalization. Why might we think that optimization is a challenge for deep neural networks? And what do I mean by optimization, actually? So optimization is a problem of finding the weights that minimize the loss, right? So we're looking for some set of weights that minimizes the loss function. Now we just described that we can compute that by back propagation. It's true, as Ben mentions, that when we have more units, it's more expensive to compute these gradients moving backwards just because there are more of them. But that's not the only concern. Actually, a bigger concern is, well, if you look at the loss landscape, like the loss function of a neural network, it doesn't look anything close to convex. This is actually, it's kind of difficult to actually visualize the loss function of a highly dimensional neural network because we only have a few dimensions for visualization. This is from a paper that tries to visualize the loss function of some popular deep neural networks by taking like a slice of them in two random directions. So these tend to have extremely complicated non-convex loss functions. You can see if you're trying to minimize this by gradient descent, well, it's not so obvious that you'll end up in the right place. It's not so obvious that stochastic gradient descent won't get stuck in any of these very large number of local minima. So that's a big problem with deep neural networks. The deeper the network gets, the more complicated your loss function gets, and the more difficult it becomes to actually find those weights. Okay. The other problem I mentioned is generalization. Why might we think that neural networks have a problem with generalization? Generalization is a problem of training a network that can effectively predict values for new unseen samples, meaning have a low test error rate, and not only for, let's say, samples it has already seen. Okay, so one suggestion is that maybe an increased number of layers will lead to variance. We know that in general, for every model that we've discussed so far, right, the more parameters we have to learn, and the more capacity the network has, so the more it's capable of expressing a complicated function, the more subject it is to overfitting. So we might have this concern about deep neural networks. They express extremely complicated functions, They learn very abstract, complex representations of the data. So you'd probably think they would be subject to terrible overfitting. So these are two major challenges with deep neural networks, and we'll spend a little time today discussing how to address them. Now, I'm going to warn you that if you're a person who likes everything to be like, neat, settled science, you're not going to like this class, because a lot of what I'm going to tell you about addressing these challenges is not necessarily understood very, very well. So a lot of it is very recent work, and some of it is already going out of style, so to speak. Probably in a couple of years from now, a lot of this will be kind of out of style. But I'm telling you about it anyways, even though it's not so well understood at the moment, because I want you to be able to kind of understand what's going on when you read about new work, state of the art, and so on. Okay, so let's start with optimization as a problem. Okay, so we know that the loss function of a deep neural network is very, very complicated and difficult to optimize. How do we optimize it effectively? Well, we're going to talk about a few methods. What are the decisions you make when deciding how to optimize this network? Let's say how to train this network. Okay, so one decision is learning rate. I'm going to call this a learning rate schedule. Okay. Ben says where to start. So do you mean like what to set the weights to at the beginning? Yes, okay. So what do you set the weights to? Where are you going to start on this loss surface? Right. Looking at this loss surface, you can see that, depending on where you start, you might end up in a good place or in a very, very bad place. What other decisions do we need to make? Okay. How long to train? Okay. So size of the network. So size of the network is not only related to training, it also determines the capacity of the network. So how complicated a function it can learn. But it's definitely also related to training. All right, what other decisions do we need to make? There's one very important one. So what does the output of each unit look like? Yes, exactly. So the activation function. So we mentioned a few different activation functions, and that's also a choice you have to make. So effective training of a neural network means careful selection of actually all of these. So today we're going to talk a little bit about most of these actually, and why some of the naive approaches don't necessarily work very well for deep networks, and what has been proposed instead. Okay, so we'll start with the activation functions. These were some of the candidate activation functions for a neural network. What did we say were some desirable properties for an activation function? Okay, so we said that this is not very good for an activation function at a hidden unit. Why? Okay. So if we, let's say, combine many weighted sums of this identity function, the output is still just going to be, a weighted sum of the inputs directly. It won't learn any nonlinear representation of features. So we can use this, let's say, at an output unit if we're doing a regression. But we're not going to use the identity function if we're as an activation function at hidden units. Okay. Let's look at the hypertangent and sigmoid functions next. Okay. So these are popular choices for a activation function, but they don't actually work very well for very deep networks. Why not? Well, remember that in a deep network, or in any network really, as part of your training, you're going to compute the gradient of the activation function, right? So you're computing this gradient of the activation function, and then you're going to propagate that back throughout the network. What does the gradient of these functions look like? What's the derivative of the sigmoid function in this region? Okay, so around here, it's pretty close to 0. What about in this region? So we know the derivative tells us the rate of change of a function. In this region, the rate of change is also pretty close to 0. Right? So the function itself is 1, but the rate of change of the function is close to 0. And the hypertangent has a similar behavior. So in the positive and negative region, if the input is a very large positive value or a large negative value, the derivative is close to 1. Okay, what about in the middle? So in the middle, the derivative looks like a little hill like this. Okay. So let's kind of draw it on the side. The derivative of the sigmoid around the bias is like a little bump, where for large positive outputs, large negative outputs, it gets very close to 0. Now, why is this a problem? Well, let's look back at this network. So remember, at each stage, you're doing back propagation. So you're computing a local derivative at each part, which includes, let's say, the derivative of the local activation function. And then you're also summing the backprop error, the gradients of all the upstream nodes. Right? So let's say at this unit, I'm taking the derivative of the local activation function, let's say a sigmoid, multiplying that by weighted gradients from all of these nodes. And then I'm going to pass that back to my downstream nodes, these nodes here. So what happens if you take a, let's say, small function, let's say the input of my neural network lands me somewhere around here. Right? So this is the derivative of the sigmoid. And let's say I'm somewhere over here. So my backprop is going to be kind of a small value. Right? What happens when you propagate small values backwards? So you're multiplying them at every pass. Right? So you take this very small, close to 0 value, you multiply them backwards, and you end up getting even smaller values. This is what's known as an a vanishing gradient problem. So when you have a deep network, if for a particular, let's say, set of inputs, the input to the units is either very positive or very negative, then you end up in the region where either the sigmoid or the hypertangent, which both have similar derivatives, have gradients very close to 0. And when you propagate that backwards, right, the downstream gradients will also be very close to 0. And since you're multiplying multiple quantities that are close to 0, they get even smaller. So this is a vanishing gradient problem. When you get into the saturation region of the sigmoid or the hypertangent, it effectively kills the neuron. So it doesn't really update anymore, right? Because you have very small gradients, and then you're not updating the weights. And then all of your downstream neurons are also getting those small gradients and updating the weights. Now, if you end up in a very steep part of the function where the gradient is very large, then you can have an analogous exploding gradient problem, where you're multiplying many values bigger than 1 back through the network, and your gradient gets very, very large. This is problematic, first of all, because you'll take like huge steps in your gradient descent that might be very bad. And not only that, it kind of compounds itself. So after a few iterations like this, you can end up like exceeding the size of the variable you're using to hold. So you have numerical stability issues as well. So this is what's known as an exploding gradient problem. Now, we mentioned Okay, so identity function is out because it doesn't learn nonlinear representations. Hypertangents and sigmoids work pretty well for shallow networks. They don't really work very well for deep networks because of this exploding gradient problem, and vanishing gradient problem. What about the ReLU function? What does the gradient of the ReLU look like? So what's the rate of change of the function right around here? Okay, so in this region, it's 0. What's the rate of change of the function here? Okay, so right there, the gradient is 1. So the ReLU function is much better for training deep networks because you won't have that same vanishing gradient or exploding gradient problem. Because the gradient is just going to be either 0 or 1. So it doesn't saturate in the positive region. Another benefit is that it's very fast to compute. So sigmoid requires you to compute an exponential function. Hypertangent, also complicated to compute. ReLU is just a max. It's extremely fast to compute, computationally efficient, doesn't saturate for positive inputs, and also tends to converge very fast, much faster than sigmoid or hypertangent activations. Now, does anyone notice a existing problem with these? Right, so we drew the gradient like this. We said it doesn't have any problems here. Right? What about here? You could still have a 0 gradient there. Ben asks, can it still learn nonlinear decision boundaries? Yes, it's still nonlinear because of this, right? Okay, so ReLU works great. It's fast to compute, can learn nonlinear decision boundaries. You can still end up with a problem in a deep neural networks. For the most part, you expect the inputs are going to be positive to the ReLU. And so usually you'll end up in this region, but you might sometimes have an input that puts you in this region. And what happens then? Well, in this case, it's actually even worse than with a sigmoid. Right? With a sigmoid, you had, let's say, a small but non-zero gradient. So you might have this, let's say, vanishing gradient problem where it gets smaller and smaller, but at least it wasn't 0. When a ReLU goes to 0, because it's in that negative region, it will actually just die completely. Right? So the ReLU is completely dead, not only very small, and it will propagate that 0 gradient back to all its downstream units, and they'll also die. So this is what's known as a dead ReLU. And this can happen if you're training deep networks. It's okay if you end up with like a small fraction of dead ReLUs in the network, but you might end up with a large fraction of the units in the network actually ending up dead over the course of the training process. And then your network won't continue to learn. So there are some variations on the ReLU that are designed to address this problem. One of them is called the leaky ReLU. And the leaky ReLU is this function. Okay. So it's max value of AX or X. So if X is negative, you're going to multiply it by some, let's say, alpha. So instead of having 0 here, you'll have, let's say, a small fraction of X. And when X is positive, it's just a ReLU again. And this is better because, let's try this. Okay, here we go. If you look at the gradient, well, the gradient here is not 0. It's a small value. And then the gradient here is 1 again. So it's still nonlinear, which is, of course, what you need. You need it to be nonlinear. But the gradient never goes to 0, so it doesn't die. So leaky ReLU is a good solution to the dead ReLU problem. If you monitor your network, so there's a question in chat, how can you spot and address this, let's say, dead ReLU problem? I'm going to say you don't really need to spot the vanishing gradient problem. Just don't use sigmoid or hypertangent in a deep network. But if you have a deep network and you're learning a, let's say, ReLU network, you can, let's say, monitor the training over time. And if you see that the gradients are not changing over time, you can monitor the gradients at each training step. If they're no longer updating, well, either it means your loss function is great, but if there is 0 in many parts of the network, you have dead ReLUs. So then you might decide to change to a leaky ReLU or some other variations on this. There are many, many variations of this. For example, there is a parametric ReLU where alpha is learned by the network instead of being a hyperparameter. There is like an exponential ReLU that gets rid of this discontinuity here and kind of makes this a little exponential curve. So there are all these variations, but usually the ReLU itself has great performance. And if not, we can always just go with a leaky ReLU. Okay. So activation function, done. All right. There's one other little thing that can help with propagating those gradients around the network. So besides for that, let's say choosing a good activation function to avoid the vanishing gradients. There's some networks use what's called skip connection, where you have direct connections between higher layers and lower layers. So let's say instead of just having each layer connect only to the next layer and the previous layer, you could end up with some special connections like this. Right. So these help information propagate through the network in the forward direction, and also helps gradients propagate backwards instead of having to kind of filter through multiple units in the middle. So it's kind of like an information highway for gradients to go directly back to the lower layer. So in some situations, this can also help with training deep neural networks. Okay. The next training decision I'm going to mention is actually not on this list, but we did mention it last week when we looked at our example neural network. Last week, we said that we'll often, let's say, scale our data before we start training the network. Let's take a look at why that might help. Okay. And this is true not only for a neural network, but it's especially important for a neural network just because they're so difficult to train in general. Okay. So let's imagine some data set that you're going to train by a linear classifier. Okay. So it's a binary classification problem. Okay. So we're training this network, we're training a linear classifier on this data. Okay. Now, how sensitive is my network to a small change in weights? Right. Let's compare this network to, let's say, an equivalent network that's centered at the origin. Which one is going to be more sensitive to a small change in weights? I think you can see if you think about, let's say, rotating this line. Right? Does it kind of move faster far away from the origin or close to the origin? Where does it move faster? Where is the change in the value of the line more dramatic? So a small update in the weights has a much bigger effect far from the origin. When we're doing gradient descent, we're trying to make many small changes in weights. And we don't want the whole thing to be too sensitive to a small change in weights. So you can see kind of just intuitively that having things be close to the origin helps. So the first data processing step is to remove the mean of the data. So if you have data that's kind of not centered around the origin, like this data here, we'll often zero center it by removing the mean. And that reduces the sensitivity to small changes in weights. Okay. Now we'll also often normalize. Right? So you might remember when we talked about like complicated loss functions, right? You could see that if, let's say, data is spread out much more in one direction than the other, you end up with a loss function that has these kind of ravine-like contours to match. Right? So you'll end up with loss contours that are also kind of very skewed in one direction. And those are also more difficult to learn. Okay, so very often we'll zero center the data. And then we'll also scale to have unit variance. So let's say, well, okay, I can't really draw it, but you can scale the data to have unit variance by scaling by standard deviation. Okay. Now, this is one way to do data processing. Another way that you might see often is, let's say, decorrelation. Okay. And of course, you'll remember from our examples on regularization and from our beauty in the classroom case study, then when you have correlated features, it makes the loss function look very ravine-like, right? So we looked at this in the regularization collab lecture, where we saw that if you have correlated features, you end up with kind of a whole region of the loss space where you have similar loss for very different parameter values. So another common data pre-processing step is this like decorrelation and whitening step. And these steps are just to make the loss surface much more friendly. Okay. So these are our popular data pre-processing steps. Okay. Now, whitening and decorrelation is usually applied to non-image data. For the image data, we'll, let's say, remove the mean. Sometimes we'll like compute a mean image and subtract that from all of the images. Sometimes we'll create a mean like per color. So images tend to have like a red channel, a blue channel, and a green channel. We sometimes compute the, let's say, mean red image, mean green image, and mean blue image, and subtract those. Okay, so we, let's see, we can check another item off our list. Okay, so we can choose an activation function to make the network easier to trade. We can do some pre-processing to make the loss surface more friendly. Next step is weight initialization. Okay, so your first instinct is often to initialize everything to 0. Why is that a bad idea? What would happen if we initialized all the weights and biases in our network to 0? Okay. If you initialize all the weights and biases to 0, so remember at each unit, the input to the unit is going to be the weighted sum of inputs, right? So the input to every single unit would be 0 regardless of the output, right? So if the input to the unit is 0, the output of every unit, the input to every unit will be 0 regardless of what's coming out of these input nodes. So it's not possible to learn from the input if for every type of, let's say, X values, you're getting the same input. So a 0 value doesn't work. What about a non-zero constant? Okay, so let's say I set all of the weights and biases to 0.2. Did that work? If you set all the weights and biases to 0.2, will the network see a different value for each set of inputs, or will you have the same problem as with the 0 weights? Okay, so let's look at maybe this unit, for example. Just to make the math easier, I'll set all the weights and biases to 0.1. Okay, so the input to this unit will be, let's say, 0.1 x1 plus 0.1 x2 plus 0.1. Okay. So let's say x1 is 1 and x2 is 0. The input will be 0.1 plus 0.1. If x1 is 2 and x2 is 0, the input will be 0.2 plus 0.1. So it does learn something different for every different input, or it does see a different input for every different x value. Okay. So the constant non-zero value doesn't have the same problem of zero value. It is capable of learning, but it's also not a good idea because then we have symmetry in the network. We'll have every single unit kind of learns in the same way because they all started at the same place. Right? And what you want is for the hidden units to kind of specialize. You want them to each learn, let's say, different parts of the feature space, or let's say different modes of the output. What you don't want is what's known as herding, where all of the units kind of move together with their weights moving in the same direction. So typically you want different units to have different values. Okay. So what if we initialize every weight and bias to a normal random value with a large value of sigma? Okay. So for each weight, we'll pick something from this bell curve, so we'll randomly sample here. Okay. So if you pick, let's say, a normal random value with a large value of sigma, all of your weights will have very different values. Right? So that's kind of good because you don't want them to be too symmetric. The problem here is that, well, some of these values are going to be very large. So some of these units will start with very large weights. And so if you're looking at, let's say, some nonlinear activation function, well, it's not as much of a problem with a ReLU, but if you're using a sigmoid, for example, you can end up with, let's say, vanishing gradient problems, exploding gradient problems. So you want to keep the weights in kind of a small range. So typically, we might think, okay, let's start with the normal random value with a small value of sigma. Okay. So here you'll end up with, let's say, all of your weights in a pretty small range centered around 0. They won't be exactly 0, but they'll all be kind of similar, but just different enough that you won't have herding. And hopefully they'll be kind of appropriate to put you right in the nonlinear part of your activation function. Now, this actually works really well for shallow networks. For deep networks, it's a problem because as these gradients propagate, okay, so the variance that you set at the beginning, so let's say at the beginning you set your initial weights to be, kind of nicely normalized over here. Okay. As you propagate them forward through the network, as the output of each network of each layer is used as input to the next layer, the variance changes, right? So if you take a network, initialize all the weights and biases with small normal random variables with the same variance, then apply, let's say, an input, like just all one's input. This is what the distribution of activation functions will look like at each layer. Okay. So at the output of the first layer, right, the distribution of the output is pretty reasonable. Every unit has something different. But as you propagate this through the network, what ends up happening is all of these outputs kind of collapse towards 0. So that's not desirable either. We're not going to get into details, but actually what you would like to have happen for initial weights is, well, you want the mean should be right in the middle of the activation function. And you want the variance of the activation functions to be the same across every layer. So if you take your initial weights, look at the output of activation functions across each layer, you want the variance to look similar at every layer. So there are a couple of alternative methods of, let's say, initializing weights. This is an illustration of what's known as Xavier initialization after the guy who wrote the paper on it. And this is a way of scaling the initial weights or scaling the variance that you use in the sigma parameter for the initial weights that makes the activation output variance similar across all layers. Xavier initialization is conventionally used for tan H, hypertangent. And there is another let's say, similar initialization that has a similar problem that's often used for ReLU. Okay. So training decisions. We've covered data preprocessing to make the loss surface more friendly. We've talked about activation functions that avoid our vanishing gradient, exploding gradient, other problems. We talked about weight initialization. So setting a good starting point so that your activations all start with some nice variance. Now, what about the learning rate schedule? Okay. So this all comes down to the optimizers, right? When you train a deep neural network, you're not going to be training with code you write yourself. You'll be using, let's say, a library like TensorFlow or PyTorch, and they all come with many optimizers. Now, the standard optimizer we've learned about is just, let's say, standard gradient descent, where you take either the entire network, the entire data set, or a batch of it, and you compute the gradient of the loss function with respect to the weights for every input in the batch. And then you update the weights by, let's say, some alpha times that gradient, right? And then we said for a stochastic gradient descent, you kind of, let's say, you can make that batch size be 1, right? So you can compute the estimate in only one randomly selected sample and move in the direction it indicates. And this is nice because, well, many of the individual steps will be in the wrong direction, but the progress towards the minimum occurs on average. Okay, so we can compute the gradient descent either using the entire data set at once, or we can use little batches, or we can use single samples. Now, we looked at this already when we looked at gradient descent to begin with, right? But we know that for, let's say, gradient descent where we use a large batch size, like this blue line here, the descent path is very smooth. And as a batch size decreases, the descent path gets jumpier and jumpier, right? And we looked at this when we did gradient descent earlier in the semester. Now, for neural networks, which are difficult to train, the stochastic gradient descent with a small number of samples tends to work better. And if you look at the loss surface here, right, it's kind of easy to understand, or at least kind of reasonable to understand, that if you're following a very bumpy path along the loss surface, it's easier to kind of jump out of some local minimum. So in practice, a small batch size often ends up in a better place in a neural network. On the other hand, it could be a little expensive to train. So that was the effect of batch size. Now, in neural networks, we talk about training, let's say, number of training steps in terms of epochs, okay? And that basically describes how many iterations or how many steps of the gradient descent we need to get to in order to see all the samples. So if you have, let's say, a mini batch size of 10 and 100 training samples, for example, you would need to do 10 steps of mini batches in order to see all the samples. So 10 steps per training epoch. Okay. Now, in addition to selecting the batch size, okay, so let's say the learning rate schedule, we have number of epochs. Let's add batch size to that. Okay, we also need to decide how we set the learning rate. We know if our learning rate is too small, it won't converge quickly. If the learning rate is too big, we'll end up oscillating. And with a deep neural network, as with everything else about optimization, all right, this gets much more tricky to select. One approach is to slowly reduce the learning rate over time. So let's say you have exponential decay, where you start off with a large learning rate because you want to kind of move quickly towards the optimal solution. But you assume that over time, you're going to make smaller and smaller changes. Okay, so you gradually decay the learning rate over time using, let's say, an exponential function, or let's say this function, which reduces the learning rate by 1 plus k times t. And so these are both a gradual decay with some tuning parameter k that determines how fast the decay happens. Now, this is kind of generally okay, but it doesn't work very well for very complicated loss surfaces. So it gradually decays the learning rate first of all, it's very sensitive to k. So you might, let's say, apply this decay. And let's go back to my complicated loss surface. So maybe your initial jump just like takes you here. And after that, your learning rate is so small that you never have the chance to, let's say, escape from this local minima you ended up with here. So that doesn't work very well. It also doesn't work very well for certain types of complicated gradient descent. So imagine you're in this ravine, right? So you're trying to, let's say, optimize some loss surface across these two parameters, W1 and W2. Okay. And we're told the ideal path follows this blue line here. Okay, so ideally you'd want to go here. Now, what happens when you do gradient descent? So this part of the loss surface is very steep in the W1 direction. So your gradient says, okay, go very far in the W1 direction. Meanwhile, the loss surface is not really very steep in the W2 direction, right? So the gradient says, okay, just go a little bit in the W2 direction. So you end up kind of bouncing back and forth along this ravine because the gradient descent tells you go very far in the opposite of the steep direction, right? So go very far in the opposite direction of steep ascent. And then you end up bouncing back and forth instead of kind of proceeding smoothly towards the minimum. And you could see that there isn't really any good learning rate decay that would solve this problem, right? Let's say you said, okay, I'm going to solve this problem by decaying my learning rate so that eventually I'll, have a very small learning rate. And so when I encounter this, let's say, steep change in the loss function, I'm not going to bounce all the way over there. I'm just going to move a little bit. But if your learning rate is very small, well, that means that your motion in this direction, in the W2 direction, is going to be really, really, really tiny. Because the gradient in that direction is tiny to begin with. Now you're multiplying it by a tiny learning rate. So you're not going to move very effectively at all. So when you have the loss surface that doesn't change in the same way in different directions, decaying the learning rate doesn't really help. So instead, there are a whole bunch of optimizers that use, let's say, either some history of the gradient or, let's say, first and second moments of the gradient to move more smoothly. Okay. One of these is called momentum. So one thing you might notice about, let's say, the gradients. Okay, so let's say you start here. Right? The gradient is very steep in the W1 direction. So it says, okay, move here. It's not really steep at all in the W2 direction. So you might move a little. Okay. And then you reach this point here. When you reach this point, it tells you, okay, gradient is very steep in the W1 direction again. So you move here. And then you move a little bit in W2 direction. Then you move, reset. Okay, and then you move very far in this direction. I'm very bad at drawing. Okay, you move very far in this direction again, and also a little in this direction. So one thing you might notice is that your gradients in the W2 direction are always in the same direction. But your gradients in the W1 direction keep changing directions. So first you're going right, and then you're going left. Right? So this insight is the idea behind the optimizer called momentum, or various momentum-based optimizers. Okay. What do these do? In momentum-based optimizers, every update is a linear combination of the gradient and the previous gradients. So it's like a weighted moving average of the gradient. What this means is that if the gradient keeps pointing in the same direction, you accumulate momentum in that direction. So you move faster and faster in that direction. Right? So in every iteration, we'll compute this, which is like weighted moving average of the gradient in the previous time step. Okay, so this is, let's say, the weighted moving average from the previous step, and this is the new gradient from the previous step. Okay. And you can see that if the gradients keep moving in the same direction, you accumulate momentum and move faster and faster in that direction. If the gradients are moving in different directions, then this term will kind of cancel out. So this weighted moving sum will, cancel out the opposite directions, and you don't move as fast in those directions. Right? So with momentum, right, you would recognize like, okay, I keep moving faster and faster in this direction, because every time the gradient in that direction is in the same direction. Right? Every time the gradient along W2 is in the same direction. But it's going to, let's say, dampen those oscillations in the W1 direction because they're in opposite directions, so they'll cancel each other out. So that's what momentum-based optimizers do. Now, there are some other, let's say, families of optimizers that are more interested in the magnitude of the gradient. So one of these is called RMS prop. What this does is it tracks a per parameter estimate of the square of the gradient. So basically magnitude of the gradient, but it's per feature. Okay. And it adapts the learning rate per feature. So looking at this, right, remember we said, okay, it wouldn't be a good idea to solve this problem by, let's say, decaying the learning rate. But if you could, let's say, decay the learning rate only in one direction and not the other direction, right? If you could decay the learning rate in the direction that has oscillations, but not in this direction, you could potentially follow the ideal path much more closely. So that's what RMS prop tries to do. It scales the gradient by, let's say, alpha is a learning rate. It scales the gradient by some measure of the magnitude of the gradient in that particular direction. So here's a nice animation. So this is a function known as Beal's function. It's obviously very difficult to optimize. And all of my points started over here. Let's look at what they all do. So follow the SGD line, which is the red line. Okay. You can see it's moving very slowly. Okay. So our standard stochastic gradient descent with a constant learning rate, much too slow. Okay, now look at the momentum line. So notice that the momentum line, well, it accumulates a lot of momentum in this direction. So it ends up kind of bouncing around before eventually reaching here, because the gradient was very large there. So it kind of accumulates too much velocity in that direction. Now look at the RMS prop line, which is a black line. So you can see, well, the RMS prop line scales the gradient update so that if the gradient is large, the learning rate gets a little smaller. So it moves faster than stochastic gradient descent, but doesn't bounce around. So the velocity-based techniques, and these other ones like, that are shown here are also kind of momentum-based, velocity-based techniques. They end up shooting off this lost surface with a very steep gradient and they bounce around. But the RMS prop approach, which just adapts the learning rate based on the magnitude of the gradient, just acts like a faster stochastic gradient descent. Now we'll mention one more optimizer, which is called Atom. Okay. And Atom is kind of a similar idea. It uses the weighted moving average of the mean of the gradient and also the variance of the gradient. Okay. So at each time step, it computes the first moment and the second moment of the gradient. And it uses those to scale the learning rate. So it's similar to RMS prop in that way, in that we're scaling the learning rate at each step. Okay. So that's our next set of training decisions. Okay. So you can do some data pre-processing. You can do some activation. You can choose a good activation function. You can initialize your weights appropriately so that you have the same variance of activations across all layers. And you can choose a good optimizer that has a good learning rate schedule. Also, tuning the number of epochs and the batch size can also help. Okay. The next issue we said we would discuss is generalization. And we said you might reasonably be concerned that neural networks would overfit terribly because they have so many parameters. You can see here many parameters. So the big question is, why don't neural networks overfit? Does anyone have ideas? Well, of course they do overfit, but we might expect them to overfit much worse than they really do. So now I'm going to tell you a secret. At the beginning of the semester, we talked about this, let's say, bias variance trade-off. And we showed this, let's say, kind of curve. And this curve is, in all the standard textbooks and everything. And this curve says, as the complexity or capacity of the network increases, so as the ability of the network to learn complicated functions increases, right, this is what the loss looks like. Okay, so this red line here is a training error. The purple line is a test error. Right? And we said that this happens because as you increase the capacity of the model to learn complicated functions, it starts to tune itself to noise in the data, in the training data, instead of, let's say, approximating the true function. And so eventually you reach a point where it can approximate the true function exactly, right? But it's not very good at generalizing. Now, all of this is classical ML. Okay. But it's been known for a while, actually, but didn't really become relevant until recently when we were able to train deep neural networks more effectively, that if you continue behind this region, something interesting happens. So we have a deep neural network. Well, we have a complicated model. As we keep increasing the capacity of the model, the training loss stays around 0, right? So the training loss remains very low because our model is complicated enough to fit the training data very exactly. But something interesting happens with the test data. So what happens with the test data? Well, at first, the test error increases as you increase the network capacity because it's fitting to the training data too exactly. But as you continue to increase the capacity of the network, you actually end up with a descending test error again. And you can end up with a test error that's maybe lower than kind of its minimum right there. Right? So classical ML tells us we should look for this point, this particular sweet spot, where we don't fit the training data exactly and we generalize pretty well. But with very deep networks, we have very large capacity to learn complicated abstract representations of the data. It turns out that if you keep increasing capacity and push past this point, and you push past this part here, which is known as the interpolation threshold, you can actually end up with a pretty good approximation of the true function. I'm going to try and give some intuition for why that happens. Okay, so this is our standard polynomial example. You could see the red points are polynomial data with noise. And I'm going to restart this animation. Okay, so you can see at the beginning, there's high bias. As we increase the complexity of a polynomial model, we fit the data better. And as we increase it even more, right, we start to overfit. So that's what we expect. Now I'm going to keep increasing the degree of the polynomial. And notice that it's still fitting the data perfectly, but it's not so crazy, right? It's not all over the place anymore. So we increase the complexity of the model. It's fitting the data pretty well. It's fitting the training data perfectly, but it's also approximating the true function pretty well. I'm going to start again and I'll be quiet so you can watch it. Okay, so why does this happen? Well, we know that the polynomial function has some true degree, right? we know that when the degree of the model, so the capacity of the model, is less than the degree of the true polynomial, we'll have underfitting, our performance will be bad. Now, as we increase the degree between, let's say, the true degree of the polynomial, so for the true degree of the polynomial, we'll get pretty good performance. As we increase the degree of the model between the true degree of the polynomial and the number of data points, right, we're going to start to fit more and more of the noise. But as we do that, right, so let's say you have a polynomial model whose degree is just slightly larger than the true polynomial. Right? Well, you're trying to fit the data very well. You don't have a lot of choices for functions that fit the data very well. Right? So you have some model class, which is some degree of polynomial that's slightly larger than the true degree. And you have, let's say, some set of functions in the model class, right, for different values of weights. And there is not many of them that fit the data equally well. But as you increase the degree of the polynomial and your, let's say, a set of potential candidate models gets bigger and bigger. And here, when I say candidate models, I mean, different weight values. So as you increase the degree of the polynomial and you have many more potential, functions to choose from, it turns out that under certain conditions, our stochastic gradient descent will actually select one that's pretty good. So we'll select one that fits the training data pretty well, but also approximates the true function pretty well. So this makes this function look much smoother and results in better performance. And that's why we have this, let's say, double descent curve. Okay. So as you increase the capacity of the network, up until the interpolation threshold, where it fits the training data exactly, right? At the interpolation threshold, there's just maybe one potential model that fits the data really well, the training data, and it doesn't fit the test data well at all. But as you increase the capacity even more, now you have many potential models that fit the training data very well. And the stochastic gradient descent will actually select one that does pretty well. And this has been observed for real networks. So for real neural networks and also for other machine learning models, that as you increase the capacity of the model, right, you might see your training error will decrease and then it will stay low. But your test error will decrease and then increase as you get near the interpolation threshold. And then it will start to decrease again. And this happens kind of in many ways. It happens with the capacity of the network. It happens with the training time of the network. So it's a very interesting result. It's not really so well understood at the moment, but this is our current understanding of it. So even though you might be concerned that neural networks might overfit tremendously, and you might think that you should kind of reduce the size of the network to avoid overfitting, it turns out that reducing the size of the network is not necessarily the best way to control overfitting, because reducing the size of the network, well, it affects, let's say, generalization, but it also affects how complex of a data representation you can learn. So it turns out that because of this double descent, you don't really need to reduce the size of the network in order to get good performance. You can get good performance just with some other, let's say, regularization techniques that help your stochastic gradient descent choose a good version of the model. So we said in this region, there are many versions of the model that fit the training data. We just want our optimization to choose like a good one that also generalizes. Okay, so what are our defenses against overfitting? Oops. All right, one of them is regularization. Just like our previous models, we can add a penalty on the norm of the weights. So we can use an L1 penalty, we can use an L2 penalty, we can use a combination penalty. I'm just going to reopen my notes. Okay. Another option for regularization is what's known as early stopping. So you compute the validation loss during each epoch. I don't know why this says performance. And then stop training while your validation loss hasn't improved in a while. Okay. This, of course, you run the risk of stopping too early before you've trained the network well. Now, does anyone have any intuition for why this helps? Why does this prevent overfitting? So my hand wavy intuition for this is something like this. So remember that when we initialize the weights at the beginning, we said why we want to initialize weights so that most of the units will end up like right near the middle of the activation function. And when most units are right near the middle of the activation function, if our activation function kind of looks like this, so whether it's kind of a sigmoid or a ReLU, something, right? So in the middle of the activation function, the behavior is basically linear. We know that a network that's linear just, is a very simple network. So no matter how many linear units you have, right, you only ever learn a linear output. Now, as you proceed through training, right, you start to move towards the nonlinear, let's say, regime of some of your units. And that's how you end up learning complex functions. But if you do, let's say, early stopping, some of the units in the network are still going to be in the linear region. So it's kind of like effectively reducing the capacity of the network, because some of the units are still basically in the identity part. Okay, so this is my hand wavy intuition for why it works. Another potential reason why it works is when you train a network, like a deep neural network, you don't find that all of the layers converge at an equal rate. So what tends to happen is that the early layers, which learn simple features, converge fast. And the late layers, which have the benefit of getting the most specific updates from the loss function, also converge fast. But the internal weights don't converge as fast. So early stopping kind of has some effect on that too. Okay, what else can we do to avoid overfitting? So one popular option is what's known as dropout. Okay. In dropout, for each training step, so you have some dropout probability. And in each training step, you will randomly zero out some of the neurons. Okay, so let's say you have some random probability of zeroing out any given neuron in each training step. Okay, so imagine these neurons are zeroed out. That means they don't get any inputs from the previous layer and they don't produce any outputs for the next layer. Now, in every iteration of training, you zero out a different random subset. And you only do this during training. You don't do it during testing. In testing, you actually do a kind of scaling instead. Now, why does this help? Okay. Well, one idea behind why it helps is it forces some redundancy in the network. So if you know that, let's say, at any given time, you might have some neurons, but not others, it means that, okay, so let's say you're trying to train a network to predict, is this image a cat or not? Okay. Well, in that case, if you know that at any given time, some of the units won't be available, then you need different units to learn kind of redundant measures of catness. So one unit might learn, does it have whiskers? Another unit might learn, does it have ears? Another unit might learn, does it have a tail? I'm simplifying, obviously. But it forces some redundancy because at any given time, you might not have some of the units available. Another interesting way of interpreting dropout is you can imagine, let's say, every dropout version of the network as a different network. Okay, so this is one version of the network. This is another version of the network. Okay. So you're training a bunch of different networks, but with shared parameters. So you can think of this as an ensemble of networks. And we know that an ensemble always reduces variance by kind of averaging out some noise. So a dropout network is kind of an ensemble of networks that share parameters and reduces variance somewhat. Now there's a variation on this called drop connect, which is very similar, but instead of zeroing neurons, you zero out weights. Okay, dropout, let's see. what else can you do to avoid overfitting? Another common thing you'll see is batch normalization. In batch normalization, you do your centering and scaling process again, so this whole process, in between layers, and using only the mean and the variance from that particular batch. Okay. So this is also kind of a way of introducing some randomness during training, and that also helps to reduce the variance. Okay. One more approach to reducing variance or to avoiding overfitting, and this is really, really important. It's one of the most effective ways. This is an approach known as data augmentation. In data augmentation, you take your inputs and you create many slightly varied versions of them that shouldn't affect the final class label, but that give you more samples to choose from. So for example, here I have an image of a cat, and I can produce very many versions of this cat with, let's say, different rotations, different cropping. I can change the contrast, the brightness, the color balance. So now instead of, let's say, one cat image, I can have 100 versions of this cat. So it's like a way of getting free data on which to train the network on without having to actually acquire more truly labeled data samples, which is very expensive. And we know that training on more data reduces overfitting. So I'll add that to my list. So to summarize, training deep neural networks is really complicated, but we have a lot of tools in our toolbox that we can use to kind of help us find the minimum of this very complicated loss surface more easily. Now we have one more topic for today. Okay, so I'll try to kind of introduce this intuition a little bit. And the idea behind this is as follows. Okay, so people are really good at recognizing objects and images, right? I can look at an image and immediately recognize many things. Right? Computers are not nearly that good at it. So why is that? Well, there are many, let's say, reasons why a computer would be less good at recognizing objects. One is the scene conditions, right? So for a computer, it's not necessarily obvious that, let's say, this is what is this? I don't even know what this animal is. That this is this animal, and let's say this is kind of a tree background, whatever. So there is a clutter in the background. You can have the object in different positions, a koala, thank you. You can have the object kind of in an unusual configuration. You could have it be partially blocked. It can be different sizes. You can have a nighttime image of your koala. So it's difficult for a computer to recognize, hey, these are all a koala. Not only that, right? You can have many different varieties of koala. Okay, maybe to humans, most koala bears look the same. Right? But what about all these cheers, right? So all of these objects are cheers, right? But the interclass similarity is very difficult to recognize, right? It's hard to see, let's say, what this chair has in common with this chair. And these are all things that are kind of easier for humans, much more difficult for computers. You have to identify these interclass similarities, but you also need to accommodate the differences between different classes. So it's not so obvious that, let's say, is this a chair or is it a bed? I don't know. Okay. Another reason why images are difficult is because of dimension. Right? You have a huge number of classes. So for example, take this popular data set of tiny images. They're 32 by 32 by 3. That means each image has 32 pixels wide, 32 pixels high, and it has a red, green, and blue color channel. Now, if you have just one network in a hidden layer, right, for a regular neural network, you'd need thousands of weights to accommodate that. Okay. And not only that, if you think about all of the things you might want to recognize in an image, you also have a huge number of classes, so potential things you want to classify. We also have the challenge that the object you're trying to recognize can be anywhere inside an image, right? This is a handwriting sample form from, let's say, the data collection for MNIST. Okay. The particular data you're looking for could be located anywhere in the image. So these are some reasons why computer vision is kind of somewhat difficult. And fully connected neural networks, So these are these neural networks where every unit is connected to every previous unit. Well, they don't work so well on images. So I'm going to explain a little bit more about why they don't work so well. And then we'll introduce a convolutional neural network, which has much better performance on image data and also some other types of data. Okay, so let's look at an example image. Okay, so here's an image. I'm going to draw a 9. Now, you remember during week 1, we talked about an approach to image classification, right? Where that was, the rule-based approach, where you can kind of divide this up into grids, and you look for different features in different parts of the grid, and you apply rules based on that. Now, obviously, if your image is over here, or your image is over here, or your image is here, or if your image is, rotated, or if your image is scaled, right? All of that kind of falls apart. Now, a traditional neural network kind of has the same problem, right? So your traditional neural network might consider, let's say, each of these parts of the image as an input. Let's make this a neural network node. Okay, so you would learn, let's say, a weight from each part of the input. This is actually basically what our logistic regression classifier did, right? It learned for each pixel and for each class, it learned a weight that says whether writing in that pixel is positively associated with belonging to the class. Now, of course, this works well if your data is nicely scaled and centered and so on, right? So then you might learn, like, okay, a 9 has writing in these 3 parts. So maybe these 3 weights should be large for the 9 class, but it doesn't have writing in the left or right side. So maybe let's say, okay, these weights are going to be large, but the other weights are small for the 9 class, right? And a neural network kind of builds on that. So you can maybe learn combinations, right? So you might learn, okay, either a 9 could have writing here, or maybe it also has a little tail over here. So you can kind of learn different versions of 9s, but it still has trouble if your 9 is scaled or rotated or moved to other parts of the images, right? If your 9 is kind of in a corner over here, well, it doesn't help that you learned high weights to here. So the idea here is what you really need is local information. You don't really need kind of global information about the entire image. You want to be able to look at small parts of the image at a time and look for specific features wherever they occur in the image. This is what a convolutional network does. Let's draw that. Okay, so a convolutional neural network will look something like this instead. Now I'm simplifying a little, just because this is like a very small image, just like a 3x3 image. Okay, but imagine you have this network, and you're interested in finding, let's say, a curve wherever it occurs in the image. So you take this neuron, and first you, let's say, look at these 4 parts of the image. So this square, this square, this square, and this square, right? Then you kind of move over, and you look at these 4 parts of the image. This part, this part, this part, this part, right? Then you move over again, you look at this part, and move over one more time and look at this part. So instead of being fully connected to the entire network at once, you're going to be locally connected to a small part of the image at a time. And you'll scan the image and look for the feature anywhere it occurs. So you'll produce some output as a result of kind of scanning this entire image, which depends on whether you saw the feature you're looking for anywhere in the image. This is what a convolutional network will do. Okay. So here's an illustration that's a little fancier, right? So a fully connected network on this image of Albert Einstein might, let's say, have 16 billion parameters if you have 400,000 hidden units. Okay. If you have a locally connected network with the same number of hidden units, but each of them only looks at, let's say, a 10 by 10 square at once, now you only have 40 million parameters. So you have far fewer parameters. It's much easier to train. And what's even more important is that you preserve kind of the geography of the problem. So normally if I would take an image, right, if I would take some image data, I would kind of flatten it, right? So I might take these 9 squares in this image, so these pixels, and I'll just turn them into a long row of pixels. And each of these pixels is going to be input to a neural network. So when I do this, I learn any information about the spatial arrangement of these pixels. When I have a convolutional network, I don't lose that information. So a conventional neural network, a fully connected neural network, will take, let's say, this flat version of the inputs. With a convolutional network, so the input and output of each layer has a width, a height, and a depth. Okay. So I'll take my input image, I'll preserve its width and height. Okay. And then I'll apply these convolutional filters. Okay. Now the convolutional filters will have some depth also. The image itself might also have some depth. So I could imagine I might start with an image that has a red, green, and blue channel. So I will have an input volume. Okay, so my input volume will be this width, this height, and this depth. That's my input volume. Okay. Then at each layer, I'll, let's say, apply this convolution, which we'll see in a moment, to the input tensor. And I'll produce an output that also has a height and a width and a depth. So I preserve the spatial arrangement of the image. So I can learn, let's say, features that depend on certain pixels having writing in them near one another. Let's see more about how that works. Okay, so I have actually a few types of layers in my convolutional network. I'll have convolutional layers, pooling layers, and fully connected layers. Let's start with a convolutional layer. So convolutional layer, let's say for a given image, let's take this image. Okay, so I have some width, I have some height, I have a depth of 3. Okay. Now, every convolutional layer, I'll have a series of filters. Okay. Each filter has some width and some height. It's not necessarily the same as the width and the height of the input image. And it also has a full depth. So that means the depth of the convolutional layer is the same as the depth as its input. Okay. So the input had 3 layers. So my first convolutional layer also has 3 layers. Now, during my forward pass on the network, okay, so when I'm computing the output, I might actually have more than one set of filters. Okay, so let's say I have 2 filters in this layer. Now, these let's say 2 columns of filters are part of the same layer. So that means I'm going to produce an output. Okay, what is the output dimension going to look like? Well, the output dimension will be, let's say, the width and height will be the same as the width and height of the filters, at least in this example. And the depth will be equivalent to let's say, this dimension. Okay, so I have kind of 2 sets of filters. So the output will have depth of 2. Let's make the output gray. So I'll have this input, which has some width and height, and let's say 3 channels. I'll have some number of filters in my convolutional layer, and each filter has full depth, which means I have like kind of a copy of it for each layer of input. And then the number of filters determines the volume of my output unit. Okay, now what do these filters actually do? So during each forward pass, each filter kind of slides over the image together, and we'll compute a kind of dot product, and they all work together. What does that mean? Okay, so let's say my filters are currently located at this position in the image. And let's actually, I'm going to kind of flip this up. Okay. So let's say kind of at the beginning of my first pass, here are my filters. So they're in this part of the image. I'm working with the first filter. So that means I'm going to be updating values in my first layer of the output. So this output layer corresponds to this first column of filters. This output layer corresponds to the second column of filters. Okay. Now, when I place the filters on this particular position in the image, now I'm going to compute a kind of dot product. What does that mean? Okay, so let's say at this point in time, I'm going to kind of redraw this here. The weights here in the filter are 0, 0, 1, and 1. Okay. And maybe the weights in the underlying image, sorry, not the weights, the input from the underlying image is 9, 5, 3, 0. Okay. I'm going to compute a kind of dot product here. So I'm going to take 9 times 0, 5 times 0, 3 times 1, and 0 times 1, and I'll sum that all up. Okay. And so this filter will contribute, let's say, 3 to this spot in the output volume. Then I'll do, let's say, the same thing for the next filter. Okay. So maybe the next filter has different weights, and also the next, the next channel in the input also has different weights. So maybe I'll produce a 1 here. So now I have 3 plus 1, which is 4. Okay, and maybe this one produces a 0. So now I'm left with a 4 in this particular point. Then I'm going to kind of shift all of these over. Right? And now I'm going to learn the next point. Okay, now, when I shift this over, right now there are different values in the input image. And maybe now there's 6 and an 8. So now when I shift it over, this filter is now going to contribute an 8. Right? See, I drew this output volume wrong, so you can see looking at it, I'm going to be shifting these filters over 3 times in this direction. Right. So I'm going to fill in these values. Every time I shift, I compute, let's say, the contribution of each filter towards the output unit, and then I add them all up and fill in that value. So that's what the convolutional layer does. Right. Here's an example. You can look at an animated demo at this link later if you're interested. But here you can see, for example, we're computing this part of the output volume. So it's, let's say, the first output volume, so corresponding to the first set of filters. And let's say adding this all up, okay, we can see this filter contributes, these are the only 2 non-zero terms, it contributes -4. This filter contributes, this is the only non-zero term, contributes +2. And this filter contributes, let's see, I have a -1 and a 1. Okay, I don't know how they got -1 there, but add that all up. Oh, and there's also a bias term here. Okay. You can kind of go through this animation later and see how it slides over the image to compute each part of the output volume. Okay, so that's my convolutional layer. And what this effectively does is it computes a correlation over different parts of the image. So the filter is learning to recognize, let's say, different features. And if that feature is present in the image, right, then this is kind of like a kind of correlation. If the feature is present in the image, the output of the convolution will be high. If the feature is not present in the image, if it's not a good match, then the output of the convolution will be small. So we're essentially finding local features in the image. Okay, I'm not going to go through the details of the output volume, but you can kind of work through the geometry and see that it makes sense. We have a couple of parameters for our convolutional layers. We have to decide how many pixels over do we want to slide the filter each time. So that's known as a stride. We also have to decide whether we want to use zero padding on the border. Okay, so what that does is determines how much the kind of output volume shrinks. Okay. If you don't use, let's say, zero padding on the border, you'll shrink the output volume at every successive iteration. So in order to have your output width and height the same as the input, you need to use a little bit of padding. Okay. So those are our convolutional layers. And here's an example of a visualization of what a convolutional layer might learn. So we'll look at this more on Thursday, but it's kind of learning these very like basic kind of features. So it does things like it looks for edges. It looks for edges between different colors. It looks for very basic patterns like that in the early layers. And then in later layers, it starts to look for much more complicated combinations of these. Okay, so the convention for a, let's say, convolutional neural network is you'll have some combination of, let me show you this. So you'll have convolutional layers. Now remember, we need some nonlinear activation functions. So every convolutional layer will be followed by a nonlinear activation. And then every once in a while, you'll have these pooling layers. Let me show you a pooling layer. A pooling layer basically kind of downsamples the image. Right? So you downsample the image to, let's say, a smaller pixel volume, but with the same depth. So this can, let's say, reduce the size of the image, both for reducing computation and to prevent overfitting. And typically we'll do what's called max pooling. So where's my example? Okay, here's my example. So here's an example of a max pooling. A max pooling will produce an output of the same depth. Here the depth is only 1. And it will, let's say, scan the image the same way the convolutional network or the convolutional layer did. But instead of doing a convolution on each part of the image, it's just going to take the max. Okay. So this helps us like, okay, so let's say I identify a particular feature I'm interested in, let's say, one part of the image, right? Well, in the next iteration, I don't necessarily care that much where in the image it was found, like the specific localization of the feature. I really just care that the feature was found in the image. So by downsampling, I kind of smooth that out so that it makes it easier to learn, let's say, the class or the continuous output. Okay, so you can see here, for example, in let's say this part of the image, I took the max, which was 6. Here, I pool these 4 pixels into, let's say, a max, which is 8, and so on. Okay. Now, typically, I'll end with a fully connected layer. Okay. So I'll have, let's say, some stacks of convolutional layers with a nonlinear activation, then pooling layers every so often. And then at the end, I'll have a fully connected layer. That's a layer that will, let's say, take all of these outputs and feed them into my output layer. And my output layer is still going to do, either a sigmoid function for binary classification or a softmax for multi-class classification or a linear activation for regression. Okay, so we'll talk about this more on Thursday when we have some notebooks with examples. I just want to hit on one more topic. Okay. So we said that when you're doing deep learning, right, you have some inputs, you learn some features, then you learn some very complex features, and then you learn a mapping of, let's say, features to output. Now, there's this basic idea. If you look at the features that were learned here, let's say by AlexNet. So you can see it's learning features like, let's say, edges, color changes. It's learning kind of very basic characteristics of an image. Are these features specific to, let's say, can you tell by looking at these whether we're trying to, let's say, classify handwritten digits or classify dogs or cats or classify cars versus stop signs? So these are very generic image features. Right? And even when we learn more abstract features, so as we proceed farther and farther along in the network, and we get closer to the output units, so the output units, or the layers near the output units, are learning features that are kind of more specific to the particular classification or regression task, because they're closer to the loss function. The layers early in the network are learning very fundamental basic features. The layers in the middle of the network are learning kind of abstract features that are complex features, but maybe not so specific to the particular task. So this is what brings us transfer learning. Okay, transfer learning is the following idea. Okay. So suppose I have let's say a network that I trained to learn cat versus dog. Okay, so the output of this network tells me whether, let's say, an input image is a cat or a dog. Now, when I train this network, I'll train it on lots of images of cats and dogs. Now we'll learn a lot of very basic fundamental features of images in general. So what if I now want to, let's say, distinguish between different breeds of dogs? Okay. A lot of the features that I learned for distinguishing cat versus dog are going to be very relevant for this classification task as well. So what if I take my cat versus dog network, okay, and I'm just going to take this part of the network, and I'm going to freeze it. Okay, so I'm going to take the entire first part of the network. Okay. When I say freeze it, that means that the weight parameters are not going to update anymore. Okay. Now these layers have already learned some basic fundamental features of images in general, and in the later layers of cats and dogs specifically. So I think they'll probably be pretty useful for classifying different breeds of dogs. Now, of course, I can't just, let's say, take this and output it directly to a classifier. I still need to do something to kind of tune it to the problem of different breeds of dogs. So I'm going to add some more weights at the end. Let's say I'm going to add maybe my own little layer at the end. These weights are not frozen. And now I'll feed it some labeled examples of different breeds of dogs. Okay. And when I feed it labeled examples of different breeds of dogs, the weights at the end of the network are going to be updated because they're not frozen. The weights in the first layers are not going to be updated. So I'm feeding it different breeds of dogs and photos, right? It's going to take those input photos, it's going to kind of output those very complicated features I already learned in the previous network. And then these weights are going to learn the mapping between those complicated features. Okay, so these are going to be newly learned. And I'm going to learn in these weights the very complicated mapping of the same features, but to the problem of breed of dog. Okay. What if I wanted to do an even more different problem? So what if I had my cats and dogs classifier, and now I want to train something to look at, let's say, truck versus airplane. Could I use the same approach? Well, so I can imagine that the first layers of my network still learn some very general features. Right? But the later layers learned features that are more specific to the particular task, right? So maybe the layers later on learn to identify the texture of fur, for example. That's much less useful for a truck versus airplane than it was for different breeds of dogs. So if my eventual task is more different, then I can still benefit from freezing the early layers, right? But maybe I need to learn slightly different complex features. So I'll freeze the first few layers, but I'm not going to freeze, let's say, more of the output layers. And so I can still take advantage of all the training I already did on cats versus dogs, but I have a little more training to do to learn what are the complex features that distinguish trucks versus airplanes. So this is the idea behind transfer learning. Okay, transfer learning. I use pre-trained networks. Now, in this example I showed you, I had a network I trained myself. But generally, we do transfer learning on pre-trained networks that someone else already trained on, millions of dollars worth of GPU computation, right? Huge data sets. So you might have, state-of-the-art networks with millions of parameters trained on millions of images, days of training on intensive GPUs. And these networks are very good feature extractors, right? So you take these networks, you freeze the first layers. Now, depending on how well-tuned the existing network is to your task, you might freeze most of the early layers and just put a new classification head at the output. Or you might freeze only some of the early layers and kind of let the training fine-tune that outer layers. Okay. But you use those, and then you, let's say, take your own labeled data, and you just use your own labeled data to adjust those weights. So you learn the output mapping, and you might tune these weights also, so learn slightly different complex features. Okay. So that is transfer learning. Okay, we are at the end of our time. Are there any questions before we go? Is reducing batch size only to get out of local minimum or training, or there's other way? So it's a little complicated, but in general, there are a variety of reasons why smaller batch sizes tend to find better minimums, but it's kind of out of the scope of this class. But that's one of the reasons. Any other questions? All right, very much. Thank you very much. I will see you all on Thursday. Take care.